Thank you so much. I really want to appreciate JetBrains taking the effort today to organize this. I want to thank everyone who joined us today. So I want to talk about something that I get excited about a lot, which is programming. And I want to talk about one aspect of that here. If you have any questions or comments, I request you to post them along the way. I'm not going to take any questions in the end. So I'm going to spend the next about 47 minutes talking and answering questions. And Mala has been so kind enough to say that she will come in and ask the questions when you ask them. So don't hesitate, ask questions anytime along the way. And she's going to moderate and post them or ask them along the way. So with that said, what does it really mean to be lazy? Well, when it comes to programming, one of the things that intrigues me is, how can we be really effective in what we do? And we want code that is elegant. We really like code that's expressive, less error prone, easy to maintain, easy to parallelize or optimize. But one thing that often concerns us is that P word, right? Performance. I cannot tell you how many times programmers contact me and say, hey, what about performance? Will it really run fast? Will it run slow? And we will not be talking about functional programming if it was not efficient. But how does it give us efficiency when the code we look at doesn't look like it's going to be efficient? So laziness really is about delaying execution. People call it as deferred evaluation. Now, I live in the Bear Country. I'm a big fan of mountain hiking. The two things I love in my life are programming and hiking the mountains. And when I hike the mountains, one of the things that I'm really afraid of is, I live in a bear country. What if there's a bear, that comes your way? And somebody wise once educated me and said, oh, Venkat, you don't have to worry if you ever come across a bear. And I said, how so? And they said, you don't have to run really fast. You just have to run faster than the person behind you. Well, okay, so that's basically, just for the sake of records, you're not supposed to run when you say a bear. But anyway, that kind of serves as a nice, anecdotal, metaphor to say, you don't want to run the code really fast. You just have to run it efficiently. And the best work is the one that is not done, because why bother doing work that has no value? So let's talk about that a little further. But before we do, let's talk a little bit about applicative order versus normal order. Now, computer science is a really weird and interesting field, but we give some, interesting terms that don't quite mean the words they make up. Well, what is applicative order? What does it really mean? Let's look at an example really quickly here. Suppose you write a function, let's say, called add. And this takes two values, int a and b, let's say. And in this case, I'm going to obviously return, let's say a plus b. Well, on the other hand, I have a function here called, let's call it evaluate, and that takes a value of type integer, and kind of silly, it simply returns a given value. But what if I were to write the code like this? What if I go in here and so what if I go in here and provide, in this case, let's say, the call to the evaluate function, but in this case, I'm going to say evaluate and then call add. Well, this is obvious to all us, the Java programmers. When will add be called? And it's like, of course, it's going to be called right away. And then the result of add will be passed over to the evaluate function. But why? Well, that is called applicative order. So applicative order is in the order in which it's applied. And the word applied, if you want to change it, use simple terms like in order in which it is invoked, order in which it is called. So applicative order is the order in which we call what you see is what you get. But there is also yet another way to do this, which is called a normal order. Well, what is a normal order? A normal order, well, it turns out that most programming languages in the mainstream follow the applicative order that I talked about. So when I talked about how it's called, you're kind of sitting there and saying, come on, tell me something new. That's the way the world works. Well, that's the way the world most of us know works. But it turns out normal order is rather very uncommon. In fact, it's funny they call it normal when it's actually abnormal. But what is normal order? Well, let's understand this with a little example. I'm going to write a little piece of code here and add AB is equal to A plus B. Well, Haskell is a beautiful language. It's a statically typed functional programming language, and I have the deepest respect for Haskell. So I write the evaluate function here, which takes a value and returns a value, and I have a main equal to do. Let's go ahead and say print, and I'm going to simply call evaluate add 1 and 2. So pretty much the code I wrote in Java, I'm writing here in Haskell. Now the question is, when is the add function called? Well, Haskell is a language which is absolutely lazy. You go to Haskell and say, hey, Haskell, call add. It says, why? Because I want to call evaluate and pass that. Well, then call evaluate. Okay, Haskell, call evaluate. And it says, but why? Well, because I want to call print and pass it. Well, then call print. Why do you bother me? Okay, call print. And it says, why? And you're like, because the user wants to see the result? Okay, that's a good reason. Let's do the work. Well, I'm going to say that add is not called until it is absolutely necessary. But of course, you're telling me, prove it. I love that kind of a thought. But you cannot put a print statement in Haskell. If you do, Haskell will get really angry and stare at you because functions are required to be pure unless otherwise you state so. And printing is impurity. So I was scratching my head. How do I prove this? And I never thought I would use a REPL to make a point. And that's exactly what I'm going to do right now. So I'm going to jump over here to the REPL. GHCI is the REPL for Haskell. And I'm going to say load sample.hs. I just loaded that particular program right in there. Now I'm going to say break on line number 1, let's say character number 16. So I added a breakpoint on line number 1. And obviously, as you know, line 1 is the add function. So I added a breakpoint for that function right there at the end of that function. Well, so when I step in, I want to pause and see what it does. I call the main function. Ta-da, notice that we broke. Okay, we are breaking on line number 1. Now I ask it to continue, and then of course it continues. Well, okay, I should type properly though. So continue, and you can see that it gave us a result of 3, which is what we expected. So what did I do in so many steps? I proved that add is called. And you're kind of wondering, but why? We know that it's called already because you ran and got the right result. You're right. But what if I change this to a 42? Now, when I run the code, it gave a result of 42. What would Java code, C# code, C++ code, almost any language code we write, what would it do? It would call the add function, take the pain of getting the result, send it to evaluate, only for evaluate to throw it away. What a waste. Not Haskell. So again, let's prove that. So if I go back to the command prompt right now here and go ahead and bring up the GHCI and load that program one more time, and we will simply ask it to put a breakpoint on line number 1 again, but let's call main, and notice it never stopped on that function because add was never called. So in a sense, what we just showed here is that the evaluation of add is deferred, postponed, it is lazy. So some languages are born lazy. Haskell was born at the beach with people just feeding it and silver spooning it, and it didn't have to do much work. No, just kidding. It's actually extremely efficient because it is really lazy and postpones operations. It blew my mind when I was working with Haskell that I called a function and knowing that it's not actually calling it until you really see an effect of it. And that changed my thinking. And this is one of the underpinnings of functional programming language. I'll just touch on this for a second. When people introduce functional programming, me included, we often emphasize the ideas of immutability. And if you tell people you should make the code immutable, that's like feeding vegetable to children. They don't like hearing it. But on the other hand, if we understand why immutability is important, well, because lazy evaluation cannot exist in the presence of mutability. That's why immutability is important to support laziness, and laziness leads to better performance. But what about other languages that we may use? How is that going to play a role in those languages? Well, to answer that question, let's go to Scala here for just a minute. So I'm going to create an expensive function. Let's just say that's an expensive function. It takes a simple integer, and all it's going to do is simply print out a called so we can see that it's called. And then, of course, what I'm going to do here is to simply say return n times 2. Imagine it's an expensive function. X equal to 4, but I'm going to say if x is greater than 5 and expensive function of, let's say, x is greater than 7, I'm going to simply print out, let's say, path 1. Otherwise, I'm going to print out right here path 2. Well, when I run this code, the question is, will expensive function be called? And you know the answer as a programmer, the answer is no, it will not be called. Now, why won't expensive function be called? And the answer to that question really in here is that because of short circuiting. And everybody knows about short circuiting. In fact, John McCarthy introduced this way early, one of the earlier languages, Lisp. And this is our, folklore, isn't it? Moms feed their babies and tell them as they are growing up saying, kid, watch out for short circuiting when you grow up and start programming. This is such an integral part of what we do. Well, we understand that languages optimize on short circuiting, but what if I take this out of here and say temp, and I say val temp is equal to expensive function? Will the expensive function be called now? And you probably are guessing it right and saying yes, but should expensive function be called now? And the answer is not really. Why not? Because we're not really using it. Notice that we are taking path 2, but why waste calling that function after all? That is not necessary. Well, but why did really Scala call the function? Well, Scala's argument is, what if that function has side effect? Aha, that's one of the biggest differences between Haskell and a lot of other languages. In Haskell, functions cannot have side effects unless they are explicitly declared to do so. The default is no side effect in Haskell. The default in most of the other languages we program in is that there is impurity everywhere we turn. So Scala says, you know what, if it's going to do something to cause a side effect, I better really, execute it. You can mark it with lazy, and as a result, notice now that it's no longer calling that function, and it went to path 2 automatically. However, if I change the x to 14 and execute the code now, notice that the call to that function is executed, as you can see right in here. And so it is a deferred evaluation. Just to make it abundantly clear, if I put the word here, notice the call to the expensive function happens after we bypass the here. And that's basically what we are seeing in this case. So the question is, laziness has a real, benefit, but how can we enjoy laziness in what we do? And the answer to that question is, maybe we should have languages that support laziness for us. But what about Java? Why can't we really make things effective in Java like that? So if I were to create an expensive function right here, let's simply say, here's an expensive function coming in, and I'm just returning as you would expect n times 2. Now, this is Java code, obviously, and I'm going to simply output called over here. And what am I going to do next? I want to go ahead and try out the laziness in the case of Java. So I'm going to come in here and say final int x equal to 4. If x is greater than 4, 5 and expensive, let's say, of x is greater than 7, well, then, of course, I want to simply print out, let's say, path 1. Else, I want to print out, let's say, path 2. Well, Java, being a wonderful language as it is, honors the concept of lazy evaluation, as you can see. So the expensive function was not called after all. But on the other hand, if I were to take this into a temp, and I say final, temp is equal to, int temp is equal to, and then I call that function, guess what's going to happen? It does make call to it for the same exact reason as to why Scala did as well. But I can tell Java lazy. I know for a minute you thought, oh my gosh, that's awesome. Sorry, that's not possible. So the question is, how can we do something like this in Java? So I want to step back for just a minute and say that if an award should be given in computer science, I think that award should go to one person. And this person had such an influence on our field that it affects what we do every single day. And that award merit should go to a gentleman named David Wheeler. He was a British computer scientist, and he said something that if is so profound, it affects every minute we program. And here's what David Wheeler said. He said, in computer science, we can solve almost any problem by introducing another level of indirection. This blew my mind because indirection is so important to what we do. It fundamentally changes our design, it changes our thinking. Now, the indirection is so powerful. What does indirection say? Well, rather than solving a problem, paraphrasing it, you can solve a problem which in turn can result in solving a problem. And one of the beautiful things in functional programming is we use lambdas. And I jumped out of my seat the minute I realized that lambdas are a level of indirection. This just blew my mind thinking that way. So notice what I'm going to do here. I'm going to go back to this and say, hey, don't call expensive right now. That's applicative order. Call it later on. That's normal order, by simply introducing a lambda. This is what I do with code. I look at this and say, oh, that's so awesome. Don't call it now, push it to a later time. Don't call it now, push it to a later time. The syntax kind of shows that, isn't it? So what we're going to do here is to simply say new supplier, and we can take a supplier and pass the lambda to it. And the supplier can defer the evaluation of that particular function. Now, this obviously comes from the supplier. So we can say function.supplier. And once we get a supplier, what are we going to do with it? We can then call the get for a deferred evaluation and say, evaluate that later and not really right now, if you will. This supplier of integer that we can provide to it, and we can use it. So the idea really behind this is that we can postpone evaluation to a later time. Oh, supplier is abstract, it says, so I'm not sure why that's giving me an error right there, but you get the point. So essentially what you can do here is you can create a supplier, and I'll come back to this later on, and so you can basically pass this over and say, I want to move this to a later time and defer the evaluation so I don't have to endure the pain of evaluating it right now. Now, obviously, in this case, you can specify this and say, postpone this evaluation to a later time and execute it on a call later on. Obviously, that's a supplier, so I can simply say, yeah, I got it now. So this is going to be a supplier of integer. And then, of course, I'm going to simply say temp is going to be that supplier that I want to use. And as a result, I can postpone the evaluation. So there we go. So, of course, if X is 14 and execute this code, you can see that it actually deferred the evaluation, but called it. Once again, to make the point, if you notice, if I put the word here, you can see that it calls that function only on demand and not any earlier. So in other words, lambda expressions are pretty awesome for that reason. So we talked about eager evaluation versus lazy evaluation. And lazy evaluation is where we defer evaluation until a later time, so much that we do this for a couple of reasons. Think about it this way. Suppose I give you an apple, not the computer, but the fruit. And you can do 4 things with that apple. Maybe you're hungry. You just take it as a snack right now. So you can eat it right now, or you can keep it for later. You can give it to somebody next to you and say, here you go. I think you should have this apple, or you can throw it away. So there are 4 things you can do. You can execute it now, execute it later, pass it on, or discard it, throw it away. And that's one of the benefits you get by postponing evaluation, is that you can optimize for execution on demand. And so laziness is very powerful. And laziness for us comes using lambda expressions in languages that don't natively support laziness. So I'm going to go on a little further and give some more examples of laziness, but I'm going to just pause for a little bit and see if there are any questions or comments. And I would rather, take your questions and answer them than just rant away myself. So I'm just going to yield and see if Mala has any questions to pass on to me. I'll be delighted to hear.
Hi, Venkat. So, a lot of viewers are intrigued about the tool that you're using. So, of course, we've got that covered. The other question is how, why Haskell? So, a lot of examples that you just covered, you are using Haskell. So, developers want to know why Haskell. What is it that it makes it more appropriate to the topic that you are covering?
Yeah. So I'll answer the first question really quickly. I use a very old tool here called TextMate, which runs only on the Mac. But if people are really intrigued about the editor, catch me on Twitter or drop me an email. On line number 4 is my email address. Line number 5 is my Twitter ID. I'll be more than happy to show them how you can run code in multiple languages using the editor. Talking about Haskell, I got drawn into functional programming after spending a few decades on imperative programming languages. Java was imperative and object oriented. Now, of course, Java is imperative, object oriented, and functional. So, and the other thing that I also got introduced was statically typed languages. And so when I came across Haskell, it blew my mind because Haskell is a statically typed language, but not like static typing in C++, C Sharp, or Java. And to compare Java static typing with Haskell's static typing is a disservice in a lot of ways. And so that intrigued me because a Haskell has static typing, but it has so much of type inference in it. I'll be frank about it. I failed 3 times learning Haskell. And the third time I said to myself, why am I having trouble with it? Something is wrong in the way I approach it. And that's when I realized, oh my gosh, I've been trying to put all this type information and get tangled with the syntax. I quit putting type, and because Haskell is so statically typed, it looked at me and said, kid, you finally understand what I'm about. And it was like having a, understanding. And Haskell is purely functional programming language. I have a talk on YouTube. If you Google for it, you'll find it. My talk was titled Learning from Haskell. I didn't call it Learning Haskell. The intention not to learn Haskell, but what did I learn from learning Haskell and how it makes changes to the way I write Java code and JavaScript code. This is one of the reasons I like to learn languages that I won't normally use. And another example of that is Elm. Elm is Haskell syntax, the 99%, and a little bit of F# syntax that compiles down to JavaScript. And Elm changed the way I write JavaScript. And so that's one of the reasons I like these languages. And it's because the languages change the way I think, change the way I design software as well. I'll probably take one more question or a couple if you want me to.
I think I would let you go on with your session and I would collect the most interesting ones and I would pop in again.
All right, sounds good. That's awesome. So let's talk a little bit about collections and laziness and how they actually work. And let's look at some of those details in here. Well, that's one of the intriguing parts in here is that when I was looking at Java 8, I started looking at Java 8 maybe about 2 or 3 years before Java 8 was released. And I'll be absolutely honest about it. I said to myself, big deal, Java has lambdas now. Why do I care? Because Java has lambdas, but lambdas has been around for a long time. I've used lambdas in a lot of different languages. Why should I care? And I remember, I usually write my books in about 2 weeks. I'm a person of impatience, don't have time. So I'll think about stuff a lot, and then I'll sit down and just cram through for 2 weeks. And during the 2-week period, my very kind family will literally slide food under the door while I just, ignore all hygiene and just hammer away on the keyboard for about, 16 hours a day. So I was thinking, what should I write, this year? And I was kind of looking at Java. And I came across lambdas. I didn't really care much. Then I came across streams, and I literally remember standing up and saying, oh my goodness, this changes everything. And when I wrote the book, my editor called me and said, are you sure you want to write something like this in a technical book? And I told her, hey, I live in Colorado. And she said, yeah, you're right, and hung up. But what I wrote in the book was, lambdas are the gateway drug, streams are the real addiction. Not that I have something to do with the drug culture in Colorado, but the point really is that I do believe that you get drawn into Java because lambdas are exciting, but streams are the ones, at least for me, held me really into it. So what do streams really provide in that idea? So let's look at an example of this to just get a feel for what that really means. I've got a collection of people right here, as you can see. And what I want to do here is to go to the create people. I want to do a filter and say, given a person, maybe I just want to get a person, get age is greater than, oh, let's say 30. There are people with different ages. Let's get people who are greater than 30. Then I want to say over here, a dot map, and given a person, I want to get their name. And then I want to say, get the name in uppercase, to uppercase. So you can see that I'm doing quite a bit of work in here. Then I say over here, find first. And once I get the first one, I say, or else I want to simply return no name at all. And let's go ahead and stop that. And I'm going to just, take these calls and run the code. But I'm going to also, in the very end, output done over here. But I'm interested in knowing what the result of this operation is. So I'll just go ahead and output that result to see what it returns to us. And let's see what we got back from running this little code example. So when I ran this code, you can see it tells me, okay, of course, I've got to do a stream on this. So let's go ahead and do a stream. And that's exactly the point, is the stream gives us laziness. I'm glad I made that mistake. Why did that code not work? Well, the reason is when you take a list that is returned by create people, if you execute that on the list, all this evaluation will become eager evaluation. This is one of the differences between Java and Kotlin, for example. In Java, they make all these automatically lazy because of stream. Kotlin gives you that switch. You can make it eager or you can make it lazy, and you get to decide it. In the Java, you don't have that option. That's why you cannot call this on the list, because if it were possible, that would become an eager evaluation. Or if it were lazy, it's not obvious to us, the programmers. They wanted to give a little semantical seam so you identify that you're doing something a little different. And to me, stream means laziness. So laziness really here is when I execute this code, you can see that it tells me that the first person who is older than 30 is Paula in this collection. Now, obvious question here is, oh my goodness, this is crazy, because I am going to go ahead and ask for everybody's age, and then ask for their name, then convert to uppercase, and then throw it all away. What a stupid way of writing code, we may think. Now, obviously, that would not make it efficient. Now, just to make it clear, there's a lot of languages that do exactly what I talked about. I often call them as functional style languages than functional programming languages. But Java, following the spirit of functional programming, does not evaluate unnecessary code. So to illustrate this point, if I go over to the person class right now. So let's go ahead and bring up the person class. And in the person class, in the get age, I'm going to simply say get age called for, and let's put the name right here. And in the get name, let's simply say get name called for, and let's go ahead and run the code and see what it tells us. Now, when you notice, you can see get age called so many times, but the get name was called only for Paula. Now, how intriguing. And this is one of the things we need to keep in mind. Stream does not evaluate that filter for every single element. No, it doesn't. Instead, what Stream actually does is something pretty intriguing. What Stream does is it draws this pipeline, and it keeps the pipeline, it combines, it's called fusion, and it defers evaluation until you start executing with a terminal operation. And when a terminal operation kicks in, it runs this fused code for one element at a time. We're talking about sequential evaluation, of course, one element at a time, but only as long as the terminal operation says give more. So think of this as opening a tap or a faucet, and you have the water flowing, but when you stop the water, close the faucet, there's no more water flowing. And that's exactly the point. So it's kind of like the tail wagging the dog kind of scenario. So to illustrate this point, notice it did not touch Paul, Jack, another Jack, or Jill. It only focused on minimum, to the point where if I remove this output right here, if you will, and if I were to remove this parenthesis, run the code one more time, and you notice it produced all that output and said done. However, if I just take away the terminal operation alone and re-execute the code, what's going to happen? Notice it said done, but it did not evaluate the filter, the map, or the map. Why is that? Well, imagine a boss calls you into the office on February the 1st and says, you're going to work on this very important project and it's due on April the 15th. What do you do on February 1st? You go to your desk and start on it right away, correct? I can see you laughing. No, you're not going to start on it on February 1st, nor the 2nd or the 3rd. You're probably going to start on it promptly on April the 14th, isn't it? Why? Because something is due the next day. What is that called? Efficiency. In fact, if you know that you're going to quit on March 15th, why would you waste all the time doing that stuff, especially if you're not really interested in it? So laziness is the ultimate sophistication in life. And I always want to find people who are lazy because they're going to do minimally what's needed. Don't confuse laziness with procrastination. Procrastination is not doing something you should have done. Laziness is, we use a term lazy in our work as well in agile development. We call it last responsible moment. So this is not just for programming. Last responsible moment is for what we do as well. Like you will never ever find me file my taxes before the deadline. Why would I? I'm the person sitting in front of the computer 11 p.m. on the deadline and asking, dear God, let me know if I'm going to live. I'll spend the next hour filing this stupid tax return. And that is lazy evaluation, deferred evaluation, last responsible moment. And that's what we are doing here in program. We're saying don't bother evaluating it until it's actually needed. Now, what are the benefits of doing this? One benefit is efficiency, performance. So we can make the code run really effectively by focusing on laziness. And that's one benefit definitely is performance. So we are not wasting our effort. If this collection had hundreds of thousands of objects, but we only wanted the first one to meet the criteria, we're not wasting our time and effort. How do you know, in the case of Java, whether it is lazy or eager? There's a very simple way to do it. Look at the return type of the function. If the return type of the function is a stream, it is an intermediate operation. If the return type is not a stream, then it is a terminal operation, which will trigger the evaluation of the code. So that is basically where the laziness comes in, is by postponing those. And this is one of the things to keep in mind, is that when you think of a list versus when you think of a stream, what are the differences? Well, one of the key differences between the two of them is list is a collection of data. So list is a collection of data, as we know. And I like to use the word bucket of data. But on the other hand, a stream is a collection, of course, but collection of functions, not a collection of data. So stream is an abstraction, not a data structure. So it draws a collection of these functions. And so what is it really? It's not a bucket of data, it's a pipeline of functions. That's what it really is. It's a pipeline of functions. And when you call on a stream does not evaluate every single function for all the objects in the collection and then move on to the next one. Instead, it it combines or fuses the functions and then evaluates on the data, but only on demand and as necessary. And that's one big difference. Well, that takes us to talking about one other application of lazy evaluation, which opens up door for things we have never seen before in languages like Java, which is the ability to perform infinite streams. So I'm going to take a few minutes to talk about infinite streams, but I want to just yield and see if there are any questions that you have. Now is a really good time to answer them as well. You're on mute, Mala. There you go.
Yes. Thank you. So one of the interesting questions was about debugging streams, because I understand as I'm watching the session, I really want to try it out. And I think the same is the case with all the developers who's watching the session. But what kind of holds them back is the limitations or the issues that they see with the adoption of the new practice. So the question is, using Lambda makes the code debugging very difficult.
Yeah, so I don't know how to answer that question because I don't write code with bugs. No, just kidding. So I have two answers for this, Mala. One of the, and I'll give one answer and I'll let you give the other answer. The first answer is, if you tell me hey, you're writing multi-threaded code and you're like, hey, that's great, I can write multi-threaded code. And then if you ask me, how do you debug multi-threaded code? We roll our eyes. The reason is not that we don't have a tool. The reason is debugging multi-threaded code is hard because of the non-predictive nature of the code, right? You put a breakpoint here and you say next, it goes over there, not here, because multiple threads are running. So one of the key things in debugging is not a lack of tool, but oftentimes a lack of understanding. We all are new to things in the beginning. And once we understand that, we are saying, aha, it's a lazy evaluation. So I can debug the way I normally debug, except knowing that it won't kick in until I hit the terminal function. And secondly, when we do this, of course, what we need to keep in mind is that when you're writing this code, we can take each of the functions and debug them separately. I do a lot of automated testing. I won't tell you I never debug, but I debug very differently today because I do automated testing and I would isolate those. One of the key things is never, ever, ever write a multi-line Lambda. That's a no-no for me. And people can write really bad code and have it hard to test it. But I'm going to give you the opportunity to answer the next question because it's very highly relevant. I admire the facility in intelliJ where you can visualize the execution of a stream. So why don't you let us know a little bit about it for the next, a few minutes or seconds or minutes, and then we'll move on right after that. So go ahead and take it over.
Right. So intelliJ IDEA has amazing facility where you can debug your streams. You can actually have a visual sequence of what each intermediate operation is doing to your data or the stream which is coming in. So you can see the original stream, what happens when you have the first operation, and so on and so forth. So yes.
Totally. Yeah. Thank you for saying that, because that's blew my mind when I see that. I'm like, whoa, I can actually put my cursor on that and immediately pop up this window and see the execution sequence. And you don't have to step through line by line to see what's going on. One of the nice things I like about these tools is how quickly they show me how stupid I am. And I love that kind of index, right? People talk about fail fast. I talk about knowing stupid fast is a good thing too. And immediately you can recover from that. I do TDD for that reason. And these tools like that you mentioned also makes a good sense. Okay, I'm going to switch gears right now and talk about infinite streams. And then I'll come back and take a few more questions right after that. So infinite streams are intriguing to me because it gives us a pathway to do things we never imagined to do before. So for example, I can take a stream, if you will, and if I want to take a problem, but I don't know how many values I want to generate, I can do that very nicely in here. So stream, I can say dot iterate, and I can then say, starting with the value, let's say 1, but given an element, let's say +1. Now, this is like on demand. Think of this like movies on Netflix. There are so many movies to watch, but which one are you going to watch? Well, the one that you want to watch, you can say, I want to watch one, I'm done, show me the next one, show me the next one. So it's on demand, even though there feels like there's an infinite amount of things available, but you can get them on demand. Then what I'm going to do here is to say dot filter, given an element, let's say mod 2 is equal to 0. And then I'm going to say dot map, given an element, let's say double it, and I pass the element to it. What in the world does double it do? So I'm going to say public static, let's say int double it, takes a number, but for our purpose, I'm going to simply say return n times 2, but I'm going to put little output that says called, let's say for, and then let's simply say n. Well, so all this code right here is simply saying, given all the values from 1, 2, 3, 4, all the way down, give me only the even numbers, but give me the double of them. Now, this is kind of scary because this is going to keep working for every single value. This is infinite, but it says, I will only do my work on demand. So you say dot limit, and I'm going to then say maybe limit to 10 values. And then you can say, well, even limit is really an intermediate operation. At this point, nothing has evaluated in this code so far. So if I were to just run this code right now and put a breakpoint right here, none of that code will actually execute because you have not seen a terminal operation. You can either do a limit, or in more recent versions of Java, you can also do a take while, and then you can give a condition. Given E is, let's say, less than maybe 100, right? So you can decide whether you want to limit based on a number of values, or you want to limit based on some logical value that you see. Then you can say for each system.out print line, and then you can simply ask it to print it. Now, this is rather a trivial example that I've shown you here, but the point I really wanted to make over here, and you can see how it executes through that sequence of data that you see up here, and I'm going to just limit this to maybe about 3 values, so we can see more of the output, and you can see how it goes on to compute those values and gives you 4, 8, and 12. And you can see the deferred evaluation of that logic as well. And then you can even see the sequence of that in here for the infinite evaluation. So you can change this to, let's say, for example, is even, for instance. And then, of course, in this case, if I were to say public static Boolean, let's say is even. And in this case, I'm going to simply output is even, let's say, is even called for, and then of course we'll say plus n, and return, well, we'll say n mod 2 is equal to, let's say, 0. And you can see in this case that it is going to evaluate that only on demand. So you can see the sequence of evaluation. Now, this is one of the interesting things is the computational complexity of imperative code is not different from functional style code. So when we often worry about performance, this has a ramification on it. Now, this is a trivial example, but imagine that you are producing some data based on an algorithm, and you want to say, I want to really keep producing this data, but only as and when a request comes through, and I want to make more data. Now, where does this lead us to? I'm a programmer that struggles to learn and struggles to understand where things are. And when I came across reactive programming, it really upset me because I was struggling to say, what in the world is reactive programming? And I played with it for a while, and call me silly, but my aha moment was suddenly realizing that reactive programming is really functional programming plus plus. And the reason is reactive programming is built on this notion of 2 things. One is a stream of data with lazy evaluation. So as a result, what does reactive streams really do? They deal with 2 things: functional composition plus the use of lazy evaluation. So in a sense, this is one of the reasons why it intrigues me to know about the lazy evaluation, because you see that not only in functional programming, you see that in reactive programming as well. So to summarize this, I'm going to, ask the question. If you say, hey, what is really big deal about OOP? And, we will talk about abstraction, encapsulation, all such. And eventually we will probably agree that polymorphism. So if you think about this really from the concept of object programming, polymorphism is polymorphism, they need a shorter word, is to object-oriented programming as lazy evaluation is to functional programming. So this is my realization, is that laziness is so important that without polymorphism, there is no idea of OOP. That was the reason to do OOP, is polymorphism, not inheritance. Polymorphism is the most important feature of object-oriented programming. And to me, when I was struggling to understand functional programming, it really excited me to know that it is the laziness that is the key of functional programming, because functional composition gives the ease of working with the code. So here's a way to think about it. Functional, composition reduces complexity of the code. Lazy evaluation, provides, let's say, efficiency of execution. This is why both of these concepts are extremely important, but functional programming cannot live with one and not the other. And that's why laziness is so important, because it leads to efficiency in what we do. So we got about 2.5 minutes left with us. So I want to take the time to answer any questions or comments that you may have. So I'll yield back to you, Mala.
Yes, lots of interesting questions. So one of the questions is, if streams are not distributed, that how can you use them? How can you use the streams in distributed environment?
Oh, that's a fantastic question. So here's one statement I make. Before the time of Java 8, the structure of concurrent code was very different from the structure of sequential code, right? So concurrent code was a monster. So it looked nothing like the sequential code. So what did streams do? Streams said structure of concurrent code is the same as the structure of sequential code. And this really is intriguing, because you can write the code sequentially and they can parallelize it, with a few caveats. But then what if you can make the structure of, local code structure of distributed code is the same as the structure of local code? Wouldn't that be really nice? And so stream is to concurrency as Spark is to distribution. And the concepts are really the same, but that's what you do, is you write the code locally using Spark, and then with a click of a switch, you can distribute it. It's the same map reduce concept, whether you do it with streams in a single JVM, or you start with a single JVM and then go across machines using Spark. So these ideas nicely translate to one another. And once we kind of step back behind syntax and start observing these things, we're able to map these and say, oh, look, this is the power of this idea here. And that same power is reflected in a different domain in this case. And so to me, Spark is to distribution as stream is to concurrency.
You explain the concepts in such simple language, simple analogies. I really like that. So the next question is, can you explain more of parallel streams in lazy context?
Yeah, no, don't do that together. That's a really good question, because they are contrary to each other. Lazy means don't do any work that you don't have to do. Parallel means fire on all engines, put all the resource you can with the hope of getting the results faster. So these are contradictory to each other. So streams are lazy only in sequential mode. When you are going in parallel mode, laziness doesn't make any sense at that point. I have a separate talks on, going from stream to parallel stream, and I spent 10 minutes of the talk showing how to do it, and the remaining 50 minutes telling people why not to do it, because there's a lot of these consequences we'll get into. So that's a really good question to keep in mind. Don't assume laziness always translates to stream. I kind of alluded to that in my talk earlier, to say we're only talking about sequential evaluation. That's important to keep in mind. I think we're out of time, but I would love to answer some of these questions at a later opportunity, because these are very important questions, very useful questions, and would absolutely be delighted. If anybody wants to download the code examples we saw here, you can download them from my website. That's given on line number 22. And actually, that's the same as over here if you go to downloads. So if you want to take a photo of this part, feel free to on your screen. But I'll yield to you, Mala, and answer any final questions, and then we can wrap it up.
I would have one final question for you, which I would like to take at the end of the talk. So, how much time do you have? Because we have another 7 to 8 minutes to go, 9 minutes to
I
be
have all the
precise.
time you want me to spend. Not a
Okay.
problem at all.
No, do you want to still work with your presentation, or are you done?
I'm
Because
done.
I would let you go.
We're good.
Okay,
Yes.
great. So I have lots of questions for you. Um, so, what are the use cases when lazy evaluation can be a bottleneck? So, I know you just mentioned one of them, so don't use them with a parallel stream. So, are there any other use case where the developer should be keeping that in mind?
Yeah. So one of the key things is to really get into grasp about the semantical difference. We are used to eager evaluation all the time, and the deferred evaluation may not be the right choice because of the deference. You're postponing the evaluation to a later time, and when you build this pipeline and then you pass the pipeline to somebody else, you are on the tail receiving end. And when you invoke the terminal operation, it kind of backtracks to evaluate this up here. And if there were a failure at this point, you need to be able to deal with that failure properly. And that's one of the, this is more of the pipeline issue than deferred evaluation itself, but they kind of go hand in hand, and we need to be really, aware of that. And pipelining doesn't have to be sequential pipelining. Deferred evaluation is when you call a function which calls a function which calls a function, and that call may be deferred until where it actually gets used. And at that point, this execution is not completed, and we need to wrap our head around it. So again, this goes back to the debugging question we had earlier. It's the problem is not the lazy evaluation, it's a difference in semantics. So it's not just writing the code, but really stepping back and saying, I understand the semantical difference, and your mind gets rewired to think, not just writing the code, but knowing this is a deferred evaluation. Designing around it is also more difficult because we're not used to it, and it is something that takes time and effort to design to promote that way of thinking and using as well.
Absolutely. I completely agree that understanding and a shift in a paradigm is much more difficult. So the initial part is too difficult to understand it and then to implement it and then use in probably a new design or an existing design. So the other question is, so that is probably from one of the earlier sections of your talk. Don't you think the idea of using supplier instead of lazy in case of calling more than one time has a performance problem?
Not really. So one of the things I always say is, if you have a hunch that there's a performance problem, prove it to yourself, right? And I have tried that quite a few times. I'm as motivated about this as anybody else is, and as critical about it. I would say, oh, that won't perform, and then I would start playing with it, and I cannot prove that it doesn't have a good performance. And in the end, this is what I tell people is, always prove it. And when you prove it, you always win. Because if you prove it has poor performance, you proved your point. If you couldn't prove it doesn't have performance, you came out learning, right? So we always win. We either learn or we prove our point, and both of them to me is a victory. So prove it always.
Absolutely. Makes sense. Okay, so there's a classic question which we get all the time. How do we handle exceptions in streams?
Yes. Functional programming and exception handling are mutually exclusive. They don't go hand in hand at all. I give a very silly example. Imagine a friend of yours calls you and says, I'm in the middle of a freeway and I'm in the middle lane. I have my tire blown out in my car. What should I do? The worst recommendation you can give them is blow up the freeway and drive in reverse. And that doesn't make any sense. What you would tell them is, you know, safely go to the, shoulder and exit the freeway and move
Yeah.
forward, not in reverse. So exception handling is an imperative style of programming idea. You are in a call stack, you blow up and you go back to where you started out in the try block. But
Right.
on the other hand, in the case of functional programming, you're in a pipeline. If something happens, you move forward, not in reverse. A really good example of this, I'll give you two examples. One example is the completable future in Java. Completable future is not a stream, but it's a one sequence through the stream. That's a really good way to learn from because they have a two tracks, a data track and an error track. Another example of that is the reactive stream API, where you have three channels. You have a data channel, a complete channel, but an error channel. So Java Streams is not a good example to look for exception handling. Look at completable future, look at reactive stream API.
Right. So, thank you so much. The example of the highway was amazing. So, the other question is, in lieu of using functional programming in Java using supplier, Lambda, etc., are there any known or hidden side effects in the runtime, at the runtime?
So one of the beautiful things about Java is they didn't just look at these ideas and say, "Hey, everybody wants it, we're going to do it." They actually took years to make it work really well. And one of them is Invoke Dynamic. Invoke Dynamic really optimizes how lambdas are treated under the hood. Some other languages earlier on decided to implement lambdas using anonymous inner classes. The developers behind Java knew that's not going to fly because it won't give performance. So they took actually years to devise a solution, and that was Invoke Dynamic. One of the suggestions I have is, when you write a lambda, write a small lambda, and then compile the code, then use Java P and do a minus C minus P option on Java P and take a look at the bytecode. That's a really nice way to see what it is under the hood. I'm a big fan of writing code and I get intrigued and I then take a look at the bytecode and see what it's doing. That's a really great way to learn as well.
Absolutely. Knowing what goes on behind the scenes is absolutely a great way to learn. So I would take the last question, which is, are you a lazy programmer and
Oh, I'm
how does
lazy
that
in
show
every
in
way.
practice?
I am
I
lazy in
believe that.
every way.
I believe that. So now that you're done in just one line, let me take another question. So, which is, would you share any real world use cases where lazy evaluation saves the day?
Oh, I cannot even start. I actually worked on a project very recently, and this company called me because they had seen my video on YouTube. I was blown away by this. And then they were describing the problem. And then I told them, hey, we could do it this way. This is like a initial discussion we were having. And I said, we could do it this way. And then there was a little, no, little voice in the call. I said, I'm sorry, I heard something. And the gentleman said, no, that's my boss. She said, I told you so. And she's the one who found me and asked him to call me. And the point is, we had 53 billion computations we had to perform. This is a big data project. And they called me because they thought functional programming will help them. And I worked with them on their project, shoulder to shoulder, sitting and pair programming. And I'll be honest about it. I was a little, apprehensive, a little scared because it's a huge, high volume, high data processing. And we applied lambdas, and amazing how performance stood up. And we were able to optimize the code and bring down. See, this program took nearly 14 hours to run. And the job given to us was to reduce the time to a couple of hours of execution. And we couldn't have done that without functional programming in Java. So this was a Java project, and we used Lambdas, and we had so much fun optimizing the code to improve the performance. So absolutely, I've seen it firsthand.
Absolutely. Thank you so much, Venkat. So Trisha is here, so that is to tell me, okay, the time is up.
Thank you so much for having me. Appreciate it. Thanks everyone for joining.
Amazing presentation. Thank you.